Okay, so this is the second part. We did this first part of this last time in class. Remember, we're doing virtual work to find the displacement at D. So the first part would be to find the real moments for this section. Remember, we have two loads. There's a distributed load across the whole structure and a point load. So although we could write a moment that's continuous for the distributed load, this point load is going to be a delineation between the first 6 feet we'll have a moment, and then from 6 to 20 feet we'll have a different moment. So this is the information we derived last time. So we have a expression for the moment in the first 6 feet, and then an expression for the moment from 6 to 20. So what's the next part? If we have the real moments, what's the next step in virtual work? It's in the title, virtual. So we need to find the virtual moments. So how do we do that? Well, we're looking for the displacement at D, so we're going to resolve this problem for the displacement at D. So let's see if I can fit that in here. So the virtual load. So we're going to redraw our structure. And now I'm going to put my virtual load here at the end of Unit 1. Now, can I write a moment that's valid for this whole structure? The answer is yes. So if I make a cut anywhere in there, say here, at some distance x, which side do you want to work? The right side or the left side?
Say the left side.
Well, let's say we did do the left side. What will I need if I want to work the left free body? I'll need the reactions. Can get those. Those are not super challenging. But what if I work the right side? I do not need the reactions. That's the beauty of a cantilever beam. So I'm going to go right. And this structure, this expression for the virtual moments is going to be good for the entire length of the structure. So if I draw a free body diagram with my virtual load on the top, I'm at some distance x. What's the remaining piece of my structure? 20 minus x. And then, of course, interior is going to be the positive virtual moment. So all I have to do is sum the moments at the cut. You've heard me say that a few times. Make sure it's in equilibrium. And now let's see what that is. So we're going to start off. The internal moment using right-hand rule as my sign convention is negative. And the moment created by the virtual load about the cut is also negative. That would be minus 1 with the moment arm of 20 minus x. So it looks like the virtual moment is going to be x minus 20. So that's done. So now what do we do? Well, remember, in general, the displacement, in this case at D, is the integral of the real moment, the virtual moment, divided by E and I, and integrated, right? So we have to go the entire length of the structure. Now we have to associate or take care of the fact that I have a real moment from 0 to 6, which I can match with the virtual moment. And then from 6 to 20, I have a different function that I can match with the virtual moment. What else is going on here? You'll notice that the first 12 feet of the beam, I is twice as big as the last 8 feet. So we have to take care of that too. So in effect, anything from 0 to 12, I'm going to have to divide by 2i. And then from 12 to 20, just divide by I. So that's going to be another area where I'm going to have to make an addition. So what this is going to turn out to be is an integral from 0 to 6 over e2i, right? And then again from 6 to 12, the real moment, the virtual moment, again over e2i. And then finally the last 8 feet from 12 to 20, it'll be the virtual moment, the real moment over ei. So I guess if I come back and label those M1 and M2, then M1 is good from 0 to 6, so that goes M1. And then from 6 to 20 is M2. See that? So now all you do is plug in M1 here, the virtual moment here, do that integration. From 6 to 12, you plug in M2, virtual moment, divided by 2EI. And then from 12 to 20, again M2 times this, but this time just divided by EI. So you can factor out the EIs, but you can see this one's going to be divided by 2, this one's going to be divided by 2. Now I can plug all that in there, but I think that's good enough for me.
So that's good on the test.
That would be good enough for me on the test too. You have the equations, and you've shown how the problem can be solved. Obviously, at home, given your time, you can plug those guys in and integrate them. But on the exam, I wouldn't ask you to do that. I'd ask you to stop here. Now, what I will do for you on a second sheet of paper, I won't do it on the video, but I'll post it, is I'll go ahead and plug those equations in and do the value and show you what they would be with an I of 400 and an E of 29,000 KSI. But really, I don't think it's necessary, unless you want to see it, to go through all that tedious algebra and integration just to produce a number. When really, from my point, this is the application of the idea and taking account for the variation in I and also the various values of the moments and the virtual moments. That's the skill. That's the key skill that I'm interested in. Yes?
Would you want us on the test to put label it at the moments M1 and M2?
You could. That makes this a little easier to write out. I mean, you could also just plug those equations in if you wanted to. That'd be just as good. I noticed I was running out of space here, and so I didn't want to start another sheet, so I just decided it might be easier just to subscript these and make it a little more concise. Now, your challenge, obviously, on the when you use mastering engineering, is they want a number. So your work has really just begun. And unfortunately, from this statement, which as far as I'm concerned is the most important part, to producing a numerical answer, there are so many roads to go wrong on that path that I guess I feel bad a little bit about that for homework, but I'll make it up for you on the test, where I won't ask you to do that. Or I might even say this is enough, and maybe if you have some extra time and you want to take a shot at producing a numerical value from this, I might give you some bonus points for that. So any questions about this problem conceptually and how to apply it? I mean, there's always some issues in the details of that, producing that number. I'd rather not use too much class time for that, unless you guys really want it. Do you guys want anything at all? Breakfast? Big slab of bacon? Have you seen that Arby's sandwich where they give you like a half an inch thick piece of bacon?
Pork belly.
The pork belly. Yeah, it's called bacon.
It's not cured.
Huh?
It's not cured, it's not called bacon.
You're eating pork belly that's uncured?
Yes,
What would that be?
pork belly.
That's called
Bacon.
fat, isn't
Yeah.
it?
Fat.
Yeah, fat. Yeah, that's what I thought.
Right.
All right. So we'll stop here. I guess I should have had the